we have come a long way in understanding multivariable calculus. We have talked about various interesting and important aspects of multivariable functions. The one that is next is called directional derivatives. So where does the motivation come from when we are going to talk about directional derivatives? So it simply comes from the notion of partial derivatives. So recall that if all the conditions for a function from D to R, where D is a subset of R2, are satisfied and x0 y0 is necessary kind of a point, in D we define the partial derivative of f with respect to x as this limit which is given here. So limit as h tending to 0, f of x0 plus h comma y0 minus f of x0 y0 divided by h. So we try to write this expression in a somewhat different way. So we write it as follows. So I write x0 plus h as x0 plus h times 1 and y0 as y0 plus h times 0 and rest as it is. So now I denote this point x0 y0 by p, and I denote the vector 1 0 as we have written here by e1. So these are very common notations in mathematics. So note that e1 is a unit vector, it has norm 1. So what we can say from here is that this expression is same as f of p plus h times e1. So this is a scalar product of a vector, so h is a scalar, e1 is a vector, so we have multiplied h by e1. So f of p plus h times e1 minus f of p divided by h. So fx, so which is the partial derivative of x with the partial derivative of f with respect to x at the point x0 y0, we have somehow written it in this form: f of p plus h times e1 minus f of p divided by h. Similarly, we could do the same thing with fy, which is the partial derivative of f with respect to y at the point x0 y0, which we call p, as we have just done here. So this point is p. So fy at p is given by limit as k tends to 0, f of p plus k times e2 minus f of p divided by k. What is e2? e2 is just another unit vector, 0 1, so it has norm 1. So in general, a unit vector is a unit vector in R2 is a vector that has norm 1. Now we want to somehow introduce a much more generalized notion, namely, can we replace e1 and e2 by an arbitrary unit vector of my choice or your choice or somebody else's choice? The notion that we are going to get by doing this is called the directional derivative. So what do we do is as follows. So as always, D we have a domain of a function D, which is a subset of R2, because we are talking about functions in two variables, real valued functions in two variables. So f is a function from D to R, and for the time being, let us say that x0 y0 is an interior point of D. So as when we talked about in the case of partial derivatives, we do not also need the full power of interior point here. I am going to talk about it in just a moment, but let me assume for the time being that this is an interior point, and let me go ahead by giving you the proper definition. So D is a subset of R2, f is a function, real valued function on D, and x0 y0 an interior point of D. So the function f is said to have a directional derivative along a unit vector u. So unit vector u means the vector has norm 1. So it has a directional derivative along a unit vector u at the point x0 y0, which again we are calling p if the following limit exists. So what is the limit? Just replace e1 or e2 by u in this case, and to keep the notation simple, instead of h and k I have written t here. So f of p plus t times u minus f of p divided by t, and we take the limit as t tends to 0. So if this limit exists, we say that f has a partial derivative along the direction or along the unit vector. So f has a directional derivative along the unit vector u at this point p. So in such a case, namely when the directional derivative exists along u at the point p, we say that this limit is exactly the directional derivative, and we denote it by du of f as or at the point x0 y0. So if I want to write a more explicit expression for the directional derivative along the vector, along the unit vector u, so what we are going to do, so u is a unit vector and u belongs to R2. So u is an element of R2, so it can be written as u1 comma u2. And if you just now put in all the information, you will see that the expression turns out to be as follows: f of x0 plus tu1 comma y0 plus tu2 minus f of x0 y0 divided by t. In particular, when we take u to be equal to e1, so e1 is something that we have mentioned in our previous slide. We will get back our partial derivative with respect to x, and if we replace by e2, which is also given in the previous slide, we are going to get back f of y. So let us now go forward with some properties, or let me first give you an example. So why don't we take a very simple example here: if xy equal to x square plus y square. So we have seen, we have discussed this function before when we talked about continuity and partial derivatives. So let me fix a point x0 y0 in R2. So it does not matter whether this is an interior point or not, but it is an interior point because the domain is R2. So now let u be a unit vector which is given by u1 and u2, and I want to compute the directional derivative, if it exists, of the function f along the direction u. So I do all the simplification, and the final expression turns out to be equal to 2x0 times u1 plus 2y0 times u2 plus t. But we see that as we take the limit as t tends to 0, so this guy goes to 0, and we are left with this expression 2x0 times u1 plus 2y0 times u2, and this is our directional derivative of f with respect to u at the point x0 y0. Note that in this case we have a very nice expression in this particular case, that we have got that duf at x0 y0 is the gradient of f at the point x0 y0, and we have taken the dot product with the unit vector u. So what I have forgotten is something that I wanted to tell you, that we do not really need the point P to be an interior point. So you remember when we talked about partial derivative with respect to x at a point x0 y0. So if this is x0 y0, all we wanted was a small line segment, a small horizontal line segment passing through x0 y0 to be contained inside the region D. And similarly, when we talked about partial derivative with respect to y, all we needed was a small vertical line segment passing through the point x0 y0 to be contained inside our region D. So when we talk about an rather arbitrary unit vector u, so then all we would need is a small line segment along the vector u that passes through the point x0 y0 to be contained inside D. So I have written this here. So let me now go ahead with other examples. So here is one of our favorite examples. So we have We have also talked about this example before. We have seen that this function that is given here, if xy equal to xy divided by x square plus y square, so that this expression makes sense, we have taken xy not equal to 0 0. So this function is given by this rational function when xy is not equal to 0 0 and 0 when xy is equal to 0 0. And we have seen that this function is not continuous at the point 0 0, which makes us curious about investing whether this function has partial derivative or directional derivatives along a given direction u at the point 0 0. So this is mostly our point of interest in the case of this example. So why don't we compute all the necessary information that we need to compute. So what we do is that we take f of x0 plus t times u1 y0 plus t times u2 minus f of x0 y0 divided by t. Of course we want to compute what is the limit of this expression as t tends to 0, but let us now try to simplify this expression, and if you do all the calculation correctly, you will reach this following expression u1 u2 divided by t times u1 square plus u2 square. But note that when we talk about directional derivative along a vector u, then this vector is a unit vector, so norm of this vector is 1, and consequently u1 square plus u2 square is always going to be 1. So we just put u1 square plus u2 square equal to 1. So what we get ultimately is that this limit, this expression that we have taken here is simplified to u1 u2 divided by t. And when we take t limit as t goes to 0, we can easily see that this limit exists. This limit can only exist if one of these two terms is 0. So why is that true? Because we know that this u1 and u2, they are constant. So a constant by t, the limit will exist if and only if this constant is equal to 0. Okay, so what happens if u1 is not equal to 0 and u2 is not equal to 0? Then we know that the product u1 u2 is not equal to 0. So and we also know that limit as t tends to 0, u1 u2, a constant function, this is going to be u1 u2 itself. But we know that limit as t tends to 0, 1 by t does not exist. So we must have that the numerator is equal to 0 in order to have the limit to exist. But so what we are saying is that the limit exists, or the directional derivative along the direction u at the point 0 0 exists if either u1 is equal to 0 or u2 is equal to 0. If u2 is equal to 0, then the direction is nothing but e1. So u is equal to e1, and if u1 is equal to 0, then you can easily see that u is equal to u2. So what it says is that the only directional derivatives of the function f that exist at the point 0 0 are the partial derivatives of f with respect to x and y. Okay, so let us go ahead. So we look at another function which we had seen to be not continuous. So the function is given by f of xy, which is x square times y divided by x to the power 4 plus y square if xy is not equal to 0 0, and 0 if xy is equal to 0 0. So again, as I have just mentioned, that we have seen before that this function is not continuous at the point 0 0. So that makes us curious to understand whether this function is this function does have directional derivatives along a given unit vector u at the point 0 0. So norm u is equal to 1 here. So when we want to evaluate this expression f of t u1 t u2 minus f of 0 0, just like we have done here. So what we get here is as follows. So we just put in the value of x and y. So this is our x in this case, y in this case, and we do not want t to be equal to 0, so that's not what we are looking for. So we are going to take t to be a non-zero quantity, and since this is a unit vector, so since u1 u2 is a unit vector, one of u1 and u2 must be non-zero. So t times u1 and t times u2, one of them must be non-zero. So this vector is of this form, and consequently this formula applies here. And if you compute this thing correctly, this simplifies to the expression u1 square times u2 divided by t square u1 to the power 4 plus u2 square. Now I divide, or I distinguish this limit into two cases. So I take the limit as t tends to 0. I can see that if u2 is equal to 0, then what happens? The numerator vanishes and consequently the limit is 0. But if u2 is not equal to 0, well, then then what happens is that as t tends to 0, this term becomes 0, and we are left with u1 square divided by u2. So of course, if u1 was 0, then it is going to be 0 anyway, as you can see from this expression. So what it means is that the directional derivative along any direction exists at the point 0 0, and also we see the following. So we can easily compute the partial derivatives of this function, so at the point 0 0, and consequently we can compute the gradient of the function, which is given by the tuple fx at 0 0, fy at 0 0, and we will see that the gradient is the 0 vector itself. So if u2 is not equal to 0, if u2 is not equal to 0, there is no way that that duf at the point 0 0, which is given by this expression, is going to be equal to this expression, that gradient of f 0 0 dot u. So why I am interested in this formula, that I will tell you in a moment. So here is the reason. So here is a theorem that we are interested in. So let me call it a theorem now, which I have not written. So we have seen that if we have a function which is differentiable at the point x0 y0, then the partial derivatives exist. And this theorem says that if the function is differentiable at the point x0 y0, then the directional derivative of f along any direction u at the point x0 y0 exists. And moreover, the expression, the equality that we were interested in takes place. So namely, du of f at the point x0 y0 is gradient of f at the point x0 y0, and we take the dot product of this gradient with the unit vector u. And this is very easy to prove, and you will be able to do it simply from the expression of differentiation. So all we need to understand is that the limit, so if the function is differentiable, then limit hk tending to 0 0 of the expression f of x0 plus h times y0 plus k minus f of x0 y0 minus fx at the point x0 y0 times h minus fy at the point x0 y0 times k divided by under root h square plus k square must be equal to 0. So we could take this vector to be any point of our choice. So in particular, what we are going to do here, we are going to take a particular direction. We are going to approach the point 0 0 along the direction that the unit vector u1 u2 gives me. So we join this line, and I am saying that we are going to approach 0 0 along this line. So in that case also, since the limit exists, it must be equal to 0. It must be equal to 0. So this is what we do. We take h and k as follows. We take h to be equal to tu1, k to be equal to tu2, and we see that tu1 tu2 approaches 0 0 if and only if t approaches 0. Note that the vector u1 u2 is a unit vector. So we see that this limit is equal to 0, and we again use the fact that u1 square plus u2 square is equal to 1 to come to a rather simplified limit. And we see that this limit, which is same as the expression for the directional derivative of a function f along the unit vector, or along the unit vector u1 u2, this exists, and this is given by this very simple expression. And also, if you look at the expression closely, you will see that this expression is nothing but the gradient of f at the point x0 y0 dot product with u. Now, as always in mathematics, we come across this question, that is the converse true. So what is going to be the converse? So it says that if the function is differentiable, then something happens. So what is that something? That something is that the directional derivatives must exist for all unit vectors u at the point x0 y0. And not only that, we have this equality. So what is going to be the converse? So suppose that we have a function if we have an interior point x0 y0 of the domain, and these two conditions are satisfied, that along any unit vector u, the directional derivative of f along u at the point x0 y0 exists, and at this equality is satisfied, then is it necessary that the function is differentiable? Well, unfortunately the answer is no. And here is an example, or strictly speaking, here is a counter example, as we often say in mathematics. So what is the function? This function, as you may have already guessed, will not be very simple, but let me explain this to you. So fxy is equal to 1 when 0 is less than y and y is strictly less than x square. So what is the region? So this is approximately the curve which is given by y equal to x square, and you could see that so this function is first of all defined. Okay, so when we are talking about this region, we are somehow below the parabola, the region which has been shaded in yellow before, and of course we do not take into consideration the x-axis, because I need y to be bigger than 0. So just above the x-axis, the region marked in green, so you pick any element from any tuple x0 y0 from this region, it is going to be 1, and you take any other point in R2, and fxy is going to be equal to 0 at those points. So some simple calculations now will show you that the directional derivative of f at the point 0 0, which is of course called as origin, so it is going to be equal to 0. So the key idea is given here. So if u1 is equal to 0, so in this point, so then what happens? So then t square u1 square is equal to 0, and here I wanted x square to be strictly bigger than 0, but here this is equal to 0. So then this point falls in this category 0, and it evaluates to 0. So what happens if u1 is not equal to 0? then there exists an epsilon greater than 0, such that whenever t is less than epsilon, then t u2 is bigger than t square t square u1 square. So what is this value of epsilon? You can just compute the value of t from here, and it turns out to be u2 divided by u1 square. I call this guy epsilon, and you can see that this satisfies the property which is here, and consequently this point also falls in this category, which is not this category, so this is going to be equal to 0. So as such, all we are going to say is that we are going to so when we are going to consider this limit, all we care is the value of t, which is very small, which is very close to 0. We do not mind what happens for the values of t which are far away from 0. All we care, so when we are going to talk about limit as t tends to 0, all we care is what happens when t is very close to 0. So here I have found a very small neighborhood, possibly very small neighborhood, such that this function evaluates to 0, and in particular this is also 0, so we can see that this limit always evaluates to 0. So the directional derivative exists and it is equal to 0, and if I take u to be equal to u1 and u to be equal to u2, we can also see that the partial derivatives are equal to 0. So as such, this equality is satisfied, and also the fact that the directional derivative exists, which is somewhat less information than the fact that the equality is satisfied. And you can easily see that this function is not continuous. For example, you can take a sequence 1 by n comma 1 by 2n square which converges to 0 0. However, you would see that this f of 1 by n comma 1 by 2n square is a constant sequence which has value 1 at every n, and consequently this converges to 1, but which is not equal to 0. So this function is not continuous. We have seen before that a differentiable function is continuous. So this says that this function is not continuous and hence not differentiable. So the converse of the theorem that we have just mentioned is not true. So we will come back to more properties of multivariable functions or more properties of multivariable functions in our subsequent videos.